This is the sort of projects that you get to work on as a coastal modeler or a coastal engineer. And now myself and Alex have done stints overseas. We're both back in Australia now, but it is a genuinely really good career to go and have if you want to travel the world. Now, there's one issue though. No one really calls you up just to say, yeah, hello. Usually when people call us, it's because something's broken, something's gone wrong, and we step in to try and figure out what's happened. Why is this happening? Why is there so many waves coming over this seawall that you've just built? That one there was over in North Wales, this one's over in Chile. And of course, as a public safety point of view, what happens when you start saying that there are waves overtopping a seawall? Lots of people get down there. So this is our day job, designing things that are in a really challenging environment. And for that, we use a lot of coastal models.
Hello and welcome to today's webinar on advancing coastal resilience. I'm your host, Craig Price with the International Water Training Institute. And on behalf of the Australian Water School, we'd like to welcome all of you attending today from wherever you happen to be on this planet full of coastlines, coastlines that will increasingly need our help to survive. Coastal resilience is a very relevant topic in today's world as we face challenges associated with climate change and in some cases trying to undo the mistakes of the past. So we'll hear more about that shortly from our expert presenters, Dan Roger, Ben Modra, Alex Maskell. If you can just let us know a little bit about where you're coming to us from and how long you've been in the coastal business. Over to you first, Dan.
Hi, everyone. So my name is Dan Rogers. I work with a consultancy called JB Pacific, or we're part of the JBA group, or JBA Consulting internationally. I've been at this for, I think my resume says 16 years now. I don't know where the time flies. Within Australia, I'm also affiliated with Griffith University and current chair of Engineers Australia Water Panel for Queensland as well. So yeah, that's
Excellent.
me.
All right, and over to you, Ben. Familiar face. Ben had a webinar that he shared with us on floating cars, so do check that one out. We'll put a link to that one in the YouTube description. But yeah, be sure to watch what happens when you start filling up some flumes with water that has cars floating around in them. Ben, let us know a little bit about your background.
Thanks, Craig. Ben Modra. I'm with the University of New South Wales. Been again probably about 16 years, and most of my work has really been around the laboratories, both physical modelling for coastal structures, for dams and stormwater as well. So yeah, quite a lot broadly around the water industry.
Great. And Alex, just down the street from me here in Perth, how long have you been here in this beautiful spot of the world bright and early this morning?
Thanks. Yeah, Alex here from JB Pacific. So yeah, I've just relocated to Perth a few months ago. Yeah, so I spent about the last decade working in numerical modelling, mostly in the UK, and yeah, just recently moved back over here.
Great. Well, what I'll do just briefly before we dive into Dan's presentation, I'll just share with you a website that I've set up here, hydroschool.org/coastal. And I'm putting all of the links that get referenced today onto this website. So this will be kind of a live website where we post any resources that get mentioned here about coastal. This will not be our first webinar on coastal. We've got some previous ones I'll show you here. We'll put the recording to this webinar here. I wanted to plug, though, Dan's video. We've had some YouTube stars with us before. We've had a couple of people with millions of subscribers on who have given us a little plug. I don't think that any hydraulic video ever yet has reached 10 million views, and this one is about to hit 10 million views. So watch Dan, be sure to help us push this one over the 10 million limit here, and maybe the algorithms will help feature some hydraulic modeling. So Dan might give us a little overview of what the JBA Trust does in some of their educational content. This is one of the videos they've produced. Ben will be talking to us a little bit about the facilities that we have here. I got a chance to tour these as part of the FMA conference. Excellent facilities. We've got the University of New South Wales Water Research Lab. So a couple of videos that we've got there, the Manly Hydraulics Lab right next door to them, a couple of their videos. And then some of our previous content from the TwoFlow team, excellent coastal modeling overviews. We're going to go back a little bit and give you a kind of a 101 highlight of coastal modeling in general. These are some pretty advanced modeling applications that they cover in some of those webinars. Be sure to catch those. Also, a couple of video clips here that you'll see that the team at Flow3D has helped us put together in association with some of the JBA consultants. And then some links to additional conferences and papers that might be relevant. So I'll stop my share there. What we'll do then is let's have everybody just briefly take a look at the poll questions so we can get a feel for the audience and where you're coming to us from. Maybe I'll just have Dan address this as you roll over and start into your presentation.
Great to see both government and consulting, a good share. About 60% of you guys are either from government or consulting. So that's good. I'm from consulting. I work, 80% of my work is for the government, state government, local councils or national governments as well. Looks like that there was a good spread of knowledge or experience with different coastal models. And as you'll find, there are a ton of them. So today we'll be giving, I think we'll call this a quick Coastal 101, and hopefully this is then going to lead to more coastal modelling courses through the Australian Water School. But first, a little bit about us. This is the sort of projects that you get to work on as a coastal modeller or a coastal engineer. Now myself and Alex have done stints overseas. We're both back in Australia now, but it is a genuinely really good career to go and have if you want to travel the world. Now, there's one issue though. No one really calls you up just to say, yeah, hello. Usually when people call us, it's because something's broken, something's gone wrong, and we step in to try and figure out what's happened. Why is this happening? Why is there so many waves coming over this seawall that you've just built? That one there was over in North Wales, this one's over in Chile. And of course, as a public health safety point of view, what happens when you start saying that there are waves overtopping a seawall? Lots of people get down there. So this is our day job, designing things that are in a really challenging environment. And for that, we use a lot of coastal models. There are a lot that we go to. So I think maybe in the flood world, there's, let's say 3 or 4 models. Coastal models, we're probably talking at least 10 that's on our shelf. We'll use them for different reasons. Coastal extremes, so like we just saw, we're looking at waves, storm surges, and cyclones or typhoons, depending on where you are. Coastal processes, so not the extremes, will go to a different model. Right? That's your tides, currents, and water levels. If there's any sort of sand involved, we have to go and pick up a different model or add modules onto our other models. And that's either sand or mud or coastline shape. That's a whole different set of modeling. Coastal designs, lots of overtopping in our sort of work, but also structural response as well. And nature-based, I've got optioneering there, could be nature-based design as well. There's a new couple of models we're using to help optimize the design. And don't get me wrong, nature-based engineering or nature-based solutions still have to have some thought put into them. I've got a list here, and we're going to be running through today in rather swift speed most of these models. Now, the ones in blue, I've flagged the ones that are, we'll call them free-ish. Swan, a wave model, absolutely free. You can go and download it now. In fact, what we might do, we can keep throwing over to Alex in the chat. Alex could almost, as I'm going, be putting the link of where you can go and get these free models. X-Beach was another really, really good one that's come out. You can try CFD for free, absolutely. OpenFoam is the free and open source before you get into the commercial packages. Of course, neural network overtopping, Delft 3D, sort of free if you can compile it yourself. Otherwise, go and pay a year subscription to Deltares. Genesis and X-Beach down the bottom as well. Now, free software is great, of course, but when you then start going and doing it for your day job like me, we can move into more commercial packages as well. There's already another webinar around AWS on 2Flow FV, which is a great one as well. Mic 21, all the mic suite, in addition to the other commercial packages there. So this is what we're going to run through today. So hopefully, when you get to the end of this, you're going to realize you can't just go and ask someone to build a coastal model. There's actually a wide range, and you're going to have to be a little bit more specific because every situation will use a different model. But we'll step through that. So the first one is a wave model. Swan and Mike Spectral Wave are 2 examples of this one, and we're going to call it a wave averaging model or a spectral wave model. Now, these are usually the go-to models to calculate wave energy or wave impacts along a coastline. Now, each of these models have their different uses. If you're going to go and pick up a wave averaging or a spectral wave model, you have to really be looking at how waves change slowly. How do waves get generated from wind, and how do they, the wind blowing over a large area, how does that slowly turn into wave energy? How do those waves come up and break? Slowly being the key word. Now, these models, unfortunately, there is no nice interface. Honestly, they could be run with just 20 lines of text. Now, over here, this is the actual input file on the right of my screen from a SWAN model. That's it, very matrix looking screens. It's all text based, but when you get it running, just turn this one off. This is the outputs of a spectral wave model. You can see here, nothing's happening too fast. This is a project we've done up in Bargara in Queensland near Bundaberg, and you can see it generally gets the wave processes right. You can see a little bit of the waves turning direction, either refraction or it has a shot at diffraction as well. But yeah, slow wave processes are great with a spectral wave model. If you then want to look a little bit more in detail, almost at groups of waves, like the wave sets, you can move towards a model like XBeach. Now, XBeach has come along maybe in the last 10 years. It's completely free, and it does a lot. And XBeach right now, I would say it's like the workhorse of our organization. We've really embraced it. It does sediment transport as well. And you can see here a couple of animations of sort of wave groups coming up. It's really good at understanding how high waves run up the beach. And that's going to help you go and set sort of building levels, figure out if waves are going to come up and over dunes as well. So that's XBeach. We can drop the link to where to download XBeach, or just Google it and you'll find it. Completely free, open source. All right, here is another project where we've been using this XBeach model. This time we've looked at it in like 2 dimensions, or pseudo 3D. And this is for the design project of the Maroochy Groins. These are really, really large sandbags, some of the largest sandbags in the world, up to 8 tons. If you're wondering how big 8 tons is, it's the equivalent of I think it's a black rhino standing on the shoulders of a Tyrannosaurus Rex, as the was an animal big enough, so I've had to combine the two. But we've done a lot of the design work here with XBeach, understanding how the waves are coming in and refracting, diffracting around the groins. If you want to then go in and start understanding what an individual wave does, you can use XBeach again, but you might have to then switch towards a Buznes wave model or a CFD model. And Craig was showing a couple of animations before there of the CFD. Now this one's an old one. I'm digging this one out. This is the Mike 21 Buznes wave model. This project's one I delivered up in Scotland, where waves were actually going up this creek or watercourse, and these waves were traveling hundreds of meters in. So we've switched over to the Mike BW model to try and figure out how the waves getting squeezed and funneled together and then cruising up the creek. And I think it's done a pretty good job. It was certainly a challenge. This 30-second animation is probably the result of 8 weeks of work. So that's the Buznes wave style ones. These days, CFD is probably going to be able to do this thing too. A couple more examples here where we're using the XBeach, or you could use Mike BW model, is in ports and harbors. So the good thing about these sort of models is it's really capturing diffraction processes after waves pass through structures. On the right, this is a project we've done in, that's Yamba in northern New South Wales, understanding how much wave energy is going through the breakwaters. You can see a lot of it. You can really see that the wave crests are really starting to straighten out as they enter in, and then they'll have to then turn around the end of the breakwater to get into this beach we're looking at. And over on the right, this is another project we're looking at optimizing port designs, where we can look at trying to extend some structures out into the water to offer protection for loading, onloading, offloading type activities. So SWAN would not be able to go and do these sort of things. So that's why we've had to step up the models. Now, when waves come in and hit a structure, they can get reflected, or they can go boom and cause overtopping. So we then wave overtopping models. We look towards them to figure out how much water is coming over the structure now or in the future. Now, there's another one here, which of course is physical modeling, which we'll get up to with Ben, of course. Here is a project we've delivered, myself and Alex actually, over in North Wales. Now this giant cloud looking thing on the left, that's a wave coming over the Rhyl coastal frontage before we've built the new defence. So it's absolutely monstrous. It was flooding a whole community very, very deep. Had to get their equivalent of the SES in there, the emergency services or first responders, to evacuate people. This is a really, really dangerous environment. And over probably a design process of about 3 years, we've used a lot of modeling, numerical modeling first to get the design fairly close, but you can never really sign off something that's going to cost millions to build just with numerical modeling alone. And this is the new structure that's in. And this one provides up to 1 in 200 year standard of protection with wave overtopping really limited. And that 1 in 200 year is calculated in 100 years from now. So I'll show you now just, this is, if you can still see my screen, the lab testing that we've done. Ben's going to show you the labs down in Sydney. This one was in the labs up in Queensland here, just down the road from myself. So we're looking at flumes. This is what we call a flume. This is a cross section of the design. But you may have seen a second ago, the coastline here has a really strange dogleg kink in it. So we've actually built a significant portion of the coastline there in this 2D model. You can see it's all there. The big waves are generated in the offshore. So how we've figured out the wave inputs into this physical model is through all of our numerical models. So we have had a lot of statistical analysis on the extreme waves. We then had a SWAN model that brought the waves to around where the paddle is, but you know, in real life. All of this part here was tested using the neural network empirical model. And then we put it in the lab to verify all of the results. And it gives you a lot more chance to, you can literally see us standing there looking at it and seeing how this thing is going to interact once it's in the ground. So, yep, there's there's our bucket. We're capturing a lot of the overtopping in. At the end of the day, it all comes down to a bucket, doesn't it? A lot of people around the world have gone and they've donated their physical modeling test results and they've put it into a big database. And this database can get interrogated through something called the neural network. So it's a big collaborative effort from labs all the way around the world. And this neural network tool, you can now use that to try and infer overtopping results from other physical lab testing. It's called the neural network. Again, we could post, it's free to use online. You can go in and use it yourself. We can pop the link in with the chat. So getting onto hydrodynamics, here you have to first calculate your tides and water levels and currents, and then you can then use those to figure out, you know, how fast the currents are going or how big the waves are happening. These sort of models, a hydrodynamic model, can then be coupled with morphology to figure out erosion and sedimentation. So a few examples here. This is a two-flow model. This one's two-flow classic, not two-flow FV, but very similar. And here we're figuring out inundation to a small community called Midge Point up in the Mackay coastline. So on the right-hand side of the screen, we had a big cyclone model, and this then, the hydrodynamics here then push all the waves, well, the tides and the storm surge into the little community. We've got some more animations here. This is a nice one that we've finished off up in Port Douglas to the north. I like this one because we've made the water blue, and it really helps with community education to see this sort of thing, the surges coming in and pulsating and going and attacking the rear of the community. So again, here we're using two-flow for the hydrodynamics. But otherwise, Delft 3D, Telemac for the French users out there, and Mike 21 are the other go-to ones. Now, a lot of these models, you can start adding in cyclonic conditions as well. Here's some work we've done in the South China Sea there, specifically in Hong Kong, where we can start adding in cyclonic wind forces over the top of these hydrodynamic models, and they start pushing the storm surge towards the mainland. So that's the other use of the hydrodynamic model in cyclone and typhoon modeling. once you get up to sediment transport, there's lots of different modes of sediment transport. So you can see on my little schematic here, you've got longshore sediment transport. Now that happens when waves arrive at an angle to the coast. So all you really need, and you need sand, of course. Onshore and offshore sediment transport, that's a different model again. That's something more like X-Beach, and hydrodynamics we've just sort of covered in there. So how we would do a lot of this suspended and bed load sediment transport is we first set up our hydrodynamic model, and then we add in more sediment information into it as well. So grain size, is it cohesive or non-cohesive? So basically, is it sand or is it mud? And turbidity information is really good to have in there as well. Here's an example then. If you have all of that information together, this is some work we've done down in the Gold Coast waterways, you can start predicting where sedimentation is going to happen, where you're going to have to dredge, and how you can then optimize currents to try and make sand accumulate where you want it to accumulate, where it's usually more easy to dredge and stay out of navigation channels. Now, a lot of these models can be set up very, very quickly. Now, I thought I'd show you this one. It's a project that we've done over in West Wales. This is probably about, let's say, an hour work. An hour's work, we can get a rough model up and running with global tidal harmonics. If you're using the Delft dashboard, it's really easy. From this hydrodynamic model, we can predict current speed. Now, and we can then convert current speed into bed shear stress. So the modeling process can actually happen really, really quickly. Now, I just wanted to highlight the point of me saying this is about an hour's work is because you can get these conditions vastly wrong if there is no calibration and validation data. You can really lean on models to get any range of answers. So I think there's a big emphasis here on having some sort of calibration data before you start setting up these models, or else you're almost better off using a lot of analytical equations and going back to your textbooks. So even though I sped through lots of models here, you can't replace real life data or physical testing. Now moving into beach erosion, speaking of, now you don't always have lots of data on historic storms because of the very nature of large events, they're very rare. So what we've done in the past is when we're looking at coastal erosion, we have switched back to empirical analytical equations. And the benefit of this is you can make these go, basically they're instantaneous. They're almost super, super fast. So we've coded up some of these, this Valinger equation, for example, in a Python-based model. And now instead of running it once, you can go and make it run for 30 years or even longer. And by not just predicting one large event, but predicting everything that's happened over, let's say, 30 years, you can, I think, more accurately try and link this with past observations. You can have this probabilistic framework where then you can do statistics on these models. Now, and there are many benefits of running a model not once, but 10,000 times once you move into this probabilistic framework. But if you do want to go and find a model where you can just go run and hit it and run it for one storm, again, X-Beach is a really good model for that at the moment. You can, you'll be able to see the waves going in. You have to have a lot more certainty in your boundary conditions there. So Valinger equations are, of course, published in papers and textbooks. X-Beach, again, a free model. So how we're now taking X-Beach model is we're looking at how it interacts with vegetation. You can see at the bottom here, we've been able to add dune vegetation into the model here as well to see the differences in erosion. But there's lots of really, really good research now coming out on how you can add in mangroves. And by having this built up into a model, we can now start assessing for a different wave climate, what sort of width of mangrove forest do you need to knock out, let's say, 30 or 50% of the wave energy to start, restoring those coastlines. And sorry about the animation. I've certainly got some oversized mangroves down there, but it's here to sort of demonstrate how these models are working, and you can really get the attenuation now going through a few factors in X-Beach. Now, I just triple check my timer. I've got been going for 20 minutes. The last few minutes, I'm just going to switch over and continue this talk on nature-based resilience, because just building a seawall in places, even though they have their benefits and they're absolutely necessary, there is a growing move towards nature-based resilience. Now, this great picture here, for another Western Australian connection here, is something that Matt Elliott from Damara and Seashore Engineering has sketched up before, and he's certainly a guru in this coastal space. And the point is, there is, just like there's many coastal models, there is a range of things you can do with nature-based resilience to offer more and more protection to a coast. Soft engineering, hybrid solutions, or working with nature, or different sort of categories. But a lot of it still isn't getting implemented. I put that down to 3 things. There's often a lack of case studies in areas. Some places have got lots and lots of these projects going in. Some people just need that bit of a push to get them up and running. Planning requirements are hard, and certainty in designs, if you're going into an area and saying, look, I can protect that stretch of coastline with a nature-based solution, a lot of your government clients are going to say, well, how certain are you going to be? And here, thankfully, this is the link back to the talk, modeling can help. So this is a project that we've just delivered up in, it's called the John Oxley Reserve, and I've got the address in a minute, where we're looking at how to protect this very eroding bit of bank and shoreline with a more hybrid nature-based approach. Now, the issue was actually boat wake waves, but I think this could have been a range of issues on why it was eroding, because the solution could have been the same. Now, we've taken a lot of our inspiration from New South Wales. So if you're looking around for guidance, I think New South Wales and Australia has a lot of really good stuff. And in addition to the World Bank and in fact, various other resources, New South Wales and Australia have a lot of projects in the ground, and you can go and have a look at it. And we've used our inspiration for this design from a lot of these projects we've been looking at. And you can have a look in the bottom left of my screen here, my schematic. So waves were hitting my cohesive bank and causing a lot of erosion. So we've returned that bank to a more stable grade, about a 1 and 2. Now, here is where your standard coastal engineer would have come in and added riprap or rock armor to the bank. And instead of doing that, we've shifted this rock armor offshore a bit. And the point is, we're trying to use less rock and drive that cost saving. We've made a rock fillet out there, and this is all things that we can have tested in a few of our models. Now, that rock fillet is offering that wave protection zone, and then we back that up with new planting, and we're encouraging new mangroves. Now, the point here is the bank stabilization is all through the vegetation, and the rock fillet is just there to allow the vegetation to establish. So it's a change in approach here, where really this has turned out to be a cheaper option than just putting rock armor, with a lot of other ecological benefits. This one, if the movie's coming through, this is it in after it's been constructed. We've got some temporary sandbags and things down there to offer a little bit of protection whilst those boat wake waves were coming in. We didn't have the rock fillets. We've also wrapped this one in geofabric and added that extra planting in there. But it's nice. This is it taken on low tide. You can see me with my drone there. At high tide, you won't even see these rock fillets, and we're certainly urging people to get up and have a look at that one in Southeast Queensland as a good demonstration project. In 5 years, you'll get there and you won't even know the rock fillets are there. It's going really well. In fact, we'll put this address in the chat in case anyone is in Australia or Queensland and fancies a trip. And we've got lots of mangrove propagules now growing and accumulating in this area. So it's going really good. So a bit of a summary. These are some of the wave models that are on our shelf that we use under different circumstances. And we're going to be asking for a poll a little bit later about which ones you guys would like to use and learn through the Australian Water School. And we're certainly looking at SWAN, XBeach, and the Neural Network, are 3 free, openly available bits of software that you could learn over 3 2-hour courses. There's already a lot of stuff on 2Flow FV out there as well. And again, XBeach down there can be used for multiple reasons. So we'd love to get your feedback on what sort of coastal models you'd like to learn. So that's me done.
Excellent. Well, thanks so much, Dan, for that presentation. Thanks so much to everybody who's been putting the questions in. Alex has been busy answering those questions in the background. We'll hear a little bit about the facilities right here in Australia from Ben, and see some of these physical models. And we'll have a bit of a discussion about the relevance of physical modeling in today's world of advancing hardware and software. We'll turn it over to you, and we'll come back with you in about 5-10 minutes to have our panel discussion. So over to you.
Thanks, Craig. And thanks, Dan, as well. Really good introduction there. This is a real race through. There's not a lot of time left, so I'm going to give you a really quick snapshot on physical modelling. Dan talked about the modelling itself, the broader numerical and empirical modelling, but physical modelling. The reason why we do physical modelling is really just a couple of things. As you get really close to the shore, the processes are quite complex and it's really quite hard to capture. So it's very computationally intensive to do numerical modelling the closer you get to the shore. So I think there was one study where it took 6 weeks to get an animation. So physical modelling actually is still really cost effective once you get quite close. And physical modelling really happens hand in hand with numerical modelling. So numerical modelling can bring you quite close to the shore, and then you take over with physical modelling to get that real near shore processes. The other one is that the interaction with structures or vegetation is really quite complex as well. And trying to characterise that is even harder. So you imagine a rock rubble structure. If you're trying to capture the processes of a rock being plucked out of that structure, you've got to get not only the waves, the wave interaction with the structure, you've got the interlocking of the rocks and the friction. Trying to get all of that into a numerical model is near on impossible. We also have a whole lot of things that aren't well represented in numericals, particularly with new products or new designs or new challenges. It's really quite hard to get those captured. The Pacific is a real forefront of dealing with climate change and sea level rise. So we're seeing a lot of work now there, and this is a pretty typical problem that they have. So you've got a fringing reef with very steep offshore condition onto a shallow lagoon, and then you've got the community sitting up the back. So this is a community sitting up the back with wave attack here. There's a real problem with pumping up of the lagoon, and that's quite hard to characterize numerically. So we do that in a physical model where you can see these quite complex behaviors of this wave overtopping, breaking here, and then pumping up the water level in the lagoon here. And we can characterize that quite well in the physical model. Another view of that, you can see the complexity of the detail. We'll try and get into the roughness to try and represent that reef structure there. So then going on to solutions for a location like that, we've been working with the Pacific Regional Infrastructure Fund, looking at low-cost solutions. What are the kind of things that they have on site that they can use? And a lot of the buildings are constructed with Besser blocks like this. And they've also got lots of sand, obviously, so they can fill sandbags. So we're developing design guidelines for them to do quite a local response to those kind of problems. Another new thing that's coming through is these coastal units that you can incorporate into structures to help create ecological enhancements. So these are basically create these little tide pools here that generally in the intertidal zone. This creates a habitat for benthic communities and food supply for other fish and other creatures as well. There's a whole lot of research being done around that. Our role in this so far has been really looking at the stability of these units within the rockwood abutment, and they're so far turning out to be quite good. This is looking at uplift forces. This obviously is a really complex interaction between the wave and the structure, particularly as you get like a little air pocket forms in here as the wave hits, and that creates a dramatic increase in the loading on the deck structures here. So this is a case where physical modelling is really important for capturing both the overtopping, which is quite a complex process in this unusual kind of structure, and also that loading on those as well. Still do quite a lot of fundamental research as well. So this is prototype scale experiments. This is actually sand from the beach. They're looking at what different moisture rates within the sand, how that affects the rates of erosion. So this is a kind of study that will get incorporated into something like XBeach to help guide the erosion rates that model uses. Some of the problems that we have are self-inflicted, if you like. They're the problems that we create for ourselves. So shipping's changed quite a lot. Instead of being brought in and out of harbours by tugs, ships have these bow thrusters and azipods. These are, huge. They're normal thrusters, but allows them to manoeuvre quite well. This has created a huge issue with scours. You imagine these propellers with, just a metre of underkeel clearance here, huge potential for scours. So we're working with a lot of ports around the world looking at scour protection devices. So this is, a new technology that we're testing in the basin, in our basins and our flumes to look at the stability of those under ship thrust. Along the same vein, we're also testing this is another new device. So these are rock-filled bags. So these might be 2 tons or 4 or 8 tons, protecting this embankment from thrust loads. And so we're helping develop design guidelines for their use, both ship protection, as coastal protection, bags at the back of the beach, and in riverine structures as well. I'm running out of time, so I can't really talk to this too much, but we're working on floating mangroves. This is fish passage, so looking at shooting fish back up over weirs. They're all quite important features. Well, I'll just finish on this last slide then, that about the physical model. I guess the future of it is we're seeing a lot of new instrumentation coming in that allows us to do quite a lot with things that we, measure things that we haven't been able to measure before. It makes it easier, cheaper to do the physical modelling. 3D printing is a huge thing for us as well. You see that a lot in nature-based solutions where people are printing mangroves or corals and looking at the loading on those. And I talked through quite a number of the new problems and solutions that we're seeing in the field. I think we'll leave it there, shall we, Craig?
Excellent. So what you can see, thanks again to all the attendees for asking the questions. What you can see is there's so much content we can do here. We want to know, what do you want to see more of? In general, the water school, we've been focused a lot on onshore or inland flood modeling. You look at the globe, look at that map we had of all the attendees. Coastal is something we haven't really had a lot of offerings in terms of courses, but I hope you saw from Dan's presentation and also from Ben's, there's so much that we can do here. And if you want to try this on your own, fill out that poll results in the end and just let us know what aspects of coastal modeling you'd like to undertake. We could even have a physical modeling bit where we talk about the Froude scales and things like that. And how do you set up a physical model? How do you relate that to real life? And what I'm going to do in the background here, I'm going to run a slide reel, some additional content, some great content that Ben has sent over to me. That'll be running in the background while we have a bit of a discussion here. So Dan, same question over to you. And I see there's a lot of people that commented on your presentation. If you can just maybe address maybe the most upvoted question that you see there.
Okay, yeah, the first one from Wesley. Have there been any studies conducted to assess the reduction in wave heights due to natural ecosystems? So yes. Now, how you do this is you need 2 wave gauges. You need to put one in some mangroves or around your vegetation. Then you need to put one just down the road where there's no vegetation. And you can actually see the differences. So there's a really good study out there. I tried to look for it then, I can't, but it's just known as the World Bank Waves Study. And in there, you're going to see a lot of really, really good research from Vietnam, where they've done this over 4 or 5 different mangrove forests. My rule of thumb, easy to remember, is you need about 30 meters of mangroves to knock out just 30% of the wave height. 30% of the wave height isn't probably enough. So these things do need to be wide, right? So you need a mangrove forest really. But yeah, go and look at the World Bank waves study. Type in a few more searches like nature-based resilience, and you'll find it.
There's quite a lot of work around kelp forests as well, and their contribution to reducing wave climate. And I think it's one of those unfortunate things that we've done is, we've destroyed a lot of those forests, and we've lost a lot of that benefit that we've had from kelp forests.
What we'll do, again, as I mentioned, we'll just keep a couple of these things running in the background here to show some of the ways that we approach the modeling on these. But yeah, watch those Flume videos, the wave tank videos that Dan has put together, and you'll see some pretty cool applications of this.
Okay, so XBeach, what sort of projects might use this? I think we've I had a lot of examples in there, but like I said, these days it's our workhorse. We use it for harbors, erosion, and sedimentation, all under wave processes. So I wouldn't use XBeach for a hydrodynamic suspended sediment type project. Anything involving waves, XBeach is it's really good. It really is. Great international team working on that as well. Excellent. So I'll scoot down. I'll do one more, then hand over to Ben. HEC-RAS, where does HEC-RAS fit into the suite here? And firstly, I'll caveat this. There is already, I think people have pointed out 4 additional models that I have not touched on. Like there is so many models out there. But HEC-RAS is a hydrodynamic model. I've heard that it can do something with waves, but it's essentially the flow of water. So hydrodynamics, you can do scour in it as well. So really good for scour around abutments, anything where there's moving water, not necessarily a wind-driven wave. That's HEC-RAS.
Yeah, so you got to be a little bit careful there because you would want to interface it. I think the question came through. Can you use it for the downstream boundary condition? Absolutely. You can put in a storm surge or a tide level at the downstream boundary, but the kind of time steps that you would need to be able to see an individual wave come up, typically the flood models are running at a coarser time step that you wouldn't see the level of detail that you'd need to get the attack from an individual wave. So it would be a boundary condition. You'd need to couple it with something else. It's not going to be, you're not going to use a 2D, depth averaged model out in a harbor, for example. You'll just have a level that's set, and that's your downstream boundary condition. It can come up and down dynamically, but you're not going to, watch individual waves come and attack the coastline like you could in some of the other models that Dan's shown. Ben, over to you. What do you want to hit next?
Yeah, there's a couple of questions sort of along along a similar theme. How do artificial reefs rate to protect beaches, or what are the guidelines that are out there? There are guidelines around. I find they tend to be quite general and motherhood statements as opposed to giving really good engineering guidelines. And it's such an interesting field of research at the moment. There's so much going on. This is a real passion of mine at the moment, is sort of combining our structures with the ecological benefit that they can provide and what the environment, those features, our kelp forests or our, seagrasses or seaweeds, what they do to contribute to the stability of our structures as well. And it's a really interesting and dynamic area at the moment, real growth. And I think there's a lot that will come out of that in probably the next 5 or 10 years. We'll have a much better idea of how we can incorporate those into our structures. A lot of it's just research now.
Okay. One major question then, I guess, that I kind of posed at the beginning. Given all these advances, you look at the last 5 years, and it's just crazy how far advanced. We talked last week on TwoFlow's webinar about the hardware advances and the speeds that we're getting nowadays. It's just crazy how far along we're getting with the hardware and software. Is that going to supersede physical models? Is our physical models in these labs that we're looking at here, is this like the DVD store now that you see just disappear? Or does it have a future? Is it going to stay? Are our computers going to catch up where we don't need them? What are your thoughts on that, Ben?
Yeah, I I'm not worried about it as a physical modeler. I like to see the incorporation of the two together a lot more. We sure see it in dams where they'll do parallel physical model and numerical modeling to take the benefits of both. Like neither's perfect, right? So, if you can incorporate the two together, that's the best by far. And there's still, as I showed, there's a lot of things that we still don't know how they work. There's new solutions, there's new problems. And the physical modeling space is a really important part of understanding how those things work.
Alex, did we get you back? Let's try that again if we can.
Yeah, can you hear me again?
Yes. Oh, great.
Good.
I did not want to have everybody sign off on the webinar without hearing your voice and letting you have a look at have a stab at some of these questions. I guess you could start with that same one. What do you think in terms of physical versus numerical?
Yeah, I'll add on to Ben's comment there. Obviously, as a numerical modeler, I think it's important to have both, because obviously often the numerical models we used are based on these lab experiments, and we don't, although we are trying to push when we do any sort of nature-based solutions, trying to implement measurement systems. So, in the UK, when we're kind of looking at building these, bringing in, say, like kelp farms to dissipate wave energy, we're trying to also get the agencies there to include monitoring, because at the moment all we really have is our kind of physical models, and you do need both, and we will continue to use it even as these computer models get better.
Okay, no, that's a great comment. So one more round for the questions. Dan, over to you.
Okay, so I've just got another answer here. I'm trying to find it. It's all about how, from anonymous attendee, how long do mangroves take to grow to a size that's effective? Now, I'm just putting something here in the chat. This was given to me recently. There's some really good data around on this one from the Cambridge University. I've got a link in there, and apparently some of their research says, there's a nice rule of thumb, which I'm all about, you need about a 10-year-old mangrove to be quite effective, because if they're really not that well established, they'll just get taken out by a big storm. So that's the typical guidance I'm saying. You want to have these things in and protected and be doing everything you can to nurture them and for the first 10 years.
Great. All right, Ben, anything you wanted to hit?
How do you get into coastal engineering at an entry level? I would highly recommend coastal engineering. It's a really interesting and fascinating area. Every week seems to be different. Every day seems to be different. You're looking at different problems and different ways of dealing with them. Have to have an engineering degree, of course. That's the first point. And then hit up your local engineering office and, try and work through them.
And I'll make a plug here. If you want to get into it, stay tuned, subscribe, figure out what's coming next. What we do through the Australian Water School, we will probably offer some of these, non-proprietary, open source applications initially, and we can add some others to the mix as well. But if you want to try this yourself, if you want to, do take some of these same steps, sign up for some of these courses, let us know what you want to see more of, and then next year join us for some of these courses. Dan and Alex, Ben, we'd love to have your involvement as well. Dan and Alex have mentioned some interest in helping to facilitate those. I hope you've seen from the presentations and from the answers today what kind of quality you're going to get out of that, and you'll be able to do some of this stuff yourself, and hands-on. When we do our courses, these are hands-on. We give you all the modeling software and background files that you need to be able to undertake these yourself. Alex, maybe one question, or one area of focus that we've mentioned, but probably needs a bigger mention is climate change. 10, 20, 30 years down the road, do you see the importance of our modeling efforts and our resilience efforts? Where do you see this heading in light of climate change? And maybe what we'll do is just go around and have some closing remarks as well. Just give us some closing words based on today's discussion, your career, your background, and where you think we're heading with this industry. So over to you first, Alex.
Yeah, thanks, Gray. Yeah, obviously climate change is really important, particularly in kind of the coastal resilience space. Obviously people like living on the coast, they like using the coast. Obviously with sea level rise, increase in storm conditions, that's going to become more and more difficult, more and more expensive. And so yeah, it's really important to kind of be able to model this appropriately so that councils and communities have the kind of the most information they have at hand to be able to understand those risks, and how we can potentially make communities more resilient so we can continue to use the beaches like we do. And yeah, so really important there.
All right, and we'll have more from Alex and future webinars. This is the first time we've had JBA on here. Shout out to Jeremy Ben, who's been a big advocate for training and the trust as well. Have a look at the website there, some of the cool educational tools that you can get out of it. Dan, I'll have you give closing remarks too. Maybe if you could say a little bit about the JBA Trust and what they offer, make a little bit of a plug there. And we've got links through that website that people can go to. But if anything you want to say about the mission.
Absolutely. So look, JBA, as we're known worldwide, we're an employee-owned company. We're not really in it for external shareholders or anything like that. We work around the world, and it does give us some freedom to pick the jobs we work on. But that still isn't enough for Jeremy Ben, and he has then established, completely separate to us, a charity called the JBA Trust, and that their sole focus is about undertaking new research and sharing that research publicly. So all of our JBA companies, JBP included, we all donate a significant part of all of our profit through the year into the JBA Trust. But like I said, that's separate. They're funding PhDs in this area. They make a lot of physical tools. If you guys all liked my wave tank video, we freely share the plans for that little mini wave flume. So, and we've got one built over in Perth, a couple built here around in Queensland as well. So it's all there to advance information in flooding and water. So yeah, go and look at the JBA Trust, or get in touch if you with them if you want your own wave tank. I'll give you the plans. You'll have to build it yourself.
Oh, that's great. No, those kind of educational tools can really help. We'll share in the background here. Ben, we'll have you offer the final closing remarks, but in the background, we'll share a couple of slides on some upcoming courses and webinars that you may want to get involved in. Ben, maybe make a plug for the facilities that you've got, and some of the efforts that have gone on, where the future's heading, and yeah, just give us bring it home with some closing remarks.
Well, I would give a plug for, we've got an open day coming up on the 16th. That's a Saturday morning. So if you are in Sydney and you're interested in what we do at WRL, or want to see physical modelling, great for kids. If you want to bring your kids along, if they're aspiring engineers or scientists, lots of great hands-on stuff. Come along to WRL on the 16th this month.
Yeah, kids of all ages will enjoy it. I certainly enjoyed seeing both those facilities a couple of months back. We'll try and post a few more of the things that the contents of what goes on there. Again, I was just thrilled to be able to see the actual tank where the cars get pushed around for the floodway design. So we've been highlighting today some of the coastal applications from the lab, but there's a lot of other hydraulic applications as well. So thanks so much to our presenters who come on without compensation here. This is a volunteer effort that we do when we bring you these free webinars. So thanks for helping to advance the industry in terms of coastal modeling. For everybody attending, you'll get this recording link. Do pass it along and share it through your social networks. We'd like to promote this field of study, especially given some of the challenges coming up with climate change, and the opportunities from some of that are being presented in some of these conferences about nature-based solutions. It seems like that's we need as much of that and as much research into that as we can possibly get. So don't leave without filling out the survey. Let us know what you want to see more of. We're excited to bring you more content throughout the rest of this year and next. And we'd like to have you with us along that journey and take your input into account along the way. So with that, we'll say goodbye on behalf of our presenters and panelists today. Thanks to all the attendees for your participation. We'll see you next time on the Australian Water School. Bye-bye.